Yeah, hello everyone. Thanks for joining us today. And we are going to talk today about BigO notation. And the speaker today is Joaquin. He will tell us about what is BigO notation and how we can use in our job. Again, you can ask your questions in the chat if you have them. And Joaquin, you can start.
Well, hello. Thank you for the invitation. And yes, I will be explaining a little bit of BigO notation. And just to give you a little bit of context, I'm currently an engineer working for IBAN in the dance office. And we're working in the field for about 7 years already. So we can start, I guess, from with the explanations. So the content for this talk would be based on what is BigO and why we need it, common BigO notations, properties and examples, and BigO in Java algorithms, and BigO in data structures. We'll have two breaks during the talk, one in the middle and one at the end for asking questions, and we can coming forward. Okay, so what is BigO notation? BigO notation is basically a way of describing the performance of an algorithm by analyzing its efficiency in terms of time and space complexity. BigO is commonly used in computer science to compare different algorithms and make decisions about which one is more suitable for a problem. We have sometimes when working and developing some code, some logic for a specific function or use case, we tend to choose one solution that is not the best performing one because we are like low on time, we are stressed, or we just didn't know about it. So BigO notation comes into play to help us basically identify if the current solution we created makes sense in terms of performance or not, so we can make an informed decision if we can keep the current implementation or if we need to change it. For example, coming back to the how the BigO notation is used, we usually express the performance of the algorithm using the letter O, followed by a function that represents how much the algorithm resource is using the machine based on the input size. So, and for this we use the letter N here as denoted in the PPT. For example, we have ON, which is linear complexity. We have O to the power of 2, which is also can be called n squared, or we have O logarithm of n. For just to give some examples, we'll see all the different possibilities later also. And here are some common BigO notations classifications, if you might call them like that. Starting from the one that has the best performance and time, which is constant time, O1. And basically, as you can see here, the algorithm performance remains constant regardless of the input size. And again, an example would be looking up an element in an array by its index. So why is this constant? Why is this not changing? It's because we are not iterating over any element, and every time we perform the operation on the list, every time we're getting the same time doing the same operation, and this doesn't change if we have 10 items, 20 items, or 1 million items. That's why the time is constant, and that's why it has the best performance. And usually um, our target when developing is to target this type of constant time when it comes to BigO notation. It's really hard to achieve this in a real life scenario. We're gonna see some examples of how this looks in a real time scenario later on. Okay, continuing, we have the log n. O logarithm of n. This algorithm performance increases logarithmically with the input size. A good example is the binary search algorithm when used. Another one is the finding the value. Another example is the all different types of the binary search implementation as well. They have the same complexity when it comes to BigO notation. Sorry. We also have the linear time, which is the one that probably we use the most when we are starting our career, when we are using a lot of for loops, where basically we use this in any operation when we have the need to iterate objects, to iterate lists, for example, or to iterate sets or maps using the entry set in Java, for example. And this one grows with the input size. So basically, we're gonna see more example of this also later on. But basically, if processing an input of 10 items happens in 10 seconds, then processing the twice the amount uh, will output 20 seconds of performance. So you guys can see how this will affect the actual case when you have like 1 million items. We'll just have to add that to the performance as well. Then we have the end log n, linearithmic time, which is basically a combination of both logarithmic and linear time. Is a good example of this is the merge sort and the quick sort. And last not least, we have the n square, quadratic time. And by using this algorithm, the performance is proportional to the square of the input size. An example of this is the Google sorting algorithm, selection sort and insertion sort as well, which because they probably use inside the combination of two for loops, which degrades over time, and is probably not the best way of sorting a really big input size of items or objects, depending on what you want to do. You will go normally for something like a merge sort, quick sort, for these type of things. Okay, continuing. We can see a graph of the most common functions where it depicts the time that basically the input size grows with the complexities of the algorithms. So we have the function, the first one, the constant time, which is the green one here, and we see that it's constant, like like no matter how much the input size changes, it's still the same. Then we have the blue one, which is the logarithmic ones. Is growth, but is growing close to the size of the constant one, as you guys can see here. And this is basically, for example, an algorithm like the binary search would take a huge input size and break it down in small chunks, which will greatly improve the performance. And that's why it allows for the performance to not degrade over time, like it will happen with something like linear time and then go into linearithmic and so on and so on. Then you see the linear here, which is just in the middle, like diagonally on the graph. And this is because the time that it takes is just it degrades and grows as the input size do, which affects the time. Then we have the where we start seeing basically a degradation, starting with the linearithmic here, going up in time and performance, and ending with the worst ones, the n square and n cube on the top, as you guys can see. Continue on, and here we have the self questions. Can we or something that we can call them like that. Why we should care about it? Well, um, efficient algorithms are to execute are much faster. For example, the binary search. But when we start usually programming, we don't have that kind of knowledge. So we go usually with something like already predefined, something like the API give us. But it's that's why it's good to know about this, the implementation, the consequence that would improve your kind of work during the development of the features. By knowing how a binary search works, by knowing how a quick sort works internally, because it will impact directly the output of the time of the feature you are trying to develop. Um, this may be a hard set requirement in your feature that you're developing. Like this could be a functional request from coming from the client, which basically could look like something like you need to your feature must return everything in 2 seconds, or it has to return a sorted list in 10 milliseconds or something like that. So then you will need to do a combination of things to achieve this, like not only implementing something which, for example, a binary search if you need to search something, or a quick sort if you need to sort something, but you also need to do something in the database as well, something like creating an index, which will also impact performance, and the sum of these things could help you achieve this kind of thing. So for example, here we have like uh, a good example, which says like the quicksort of an array with billion elements will take 5 minutes. This is just an approximation. It's nothing like it's not like a hard set fact, but it's an example to give some perspective. So a quicksort array in 1 billion elements will take 5 minutes. And we have on the other hand like a bubble sort would take 400 years. This is because of the degradation we talked before with the bubble sort. Which will be something like a quadratic time, and in worst case scenario, and so on with the billion elements. It will grow into completely degradation. Another example coming to, for example, a database approach. In a search in SQL DB with a billion elements by ID, it will take a few milliseconds if we have correctly created an index, but it will take 10 seconds when we don't have an index. And this will escalate quite heavily is if we have more elements. Instead of billions, we have trillions. So then we'll see here something like 50 milliseconds, 50 seconds, 60 seconds, 1 minute, and then we will have very bad conditions and something to fix in the DB. Another example here, depending on the workload, an array list can be 1 times faster than a linked list or vice versa. And this is in this point everything comes down to requirements, use cases. What is your specific use case in your feature? Why I mentioned this? Because a lot of people just say, when comparing array lists between linked list, they say it's always the array list versus the linked list. There is also the fact that it seems there are some news about the fact that maybe linked list is going to be deprecated, and there is going to be array list. But before going into that, it's more about the use case in general, because they both give you different functionality. For example, in the array list, if you want to look up elements, like if that's your main feature, that's the main thing you're going to use the array list for, then an array list would perform better than the linked list, because it gives you constant time every time you want to search an element by the index. But in the other hand, if you need to do something like look the first item and the last item of the linked list of a list, then a linked list will be a better choice for you because of the solution that already the linked list give you. So it's about that. It's about comes down to your specific use case and the requirement that your application and your feature have in that moment. Why can we exactly calculate how much time the algorithm will take to execute? Well, basically because of the conditions. We not only we are tied down to algorithms like we have mentioned till now, and conditions like the milliseconds, what the functional requirement is that the client may have, but also we are tied down about hardware conditions. For example, we don't know how many different processors or memory we have. We don't know how many different background programs are running at the moment. So we cannot like feasibly guarantee that your application will have the CPU all the time. Like the CPU is gonna focus on your application all the time. We cannot guarantee that. And also like conditions like air temperature, humidity. These conditions affect the processor speed. Why? Because if we have a hot temperature, the processor is gonna go a little bit hot and hotter. And when the processor in a computer gets hot, it's it degrades the performance of this given processor. And we usually, when it comes to empresarial solutions, we are basically using on-premise or something like an AWS approach, in which we have something like hundreds of computers provided by the autoscale policy. For example, a simple example, when using AWS, you have an autoscale policy and you need to scale out. So a different box just pop out and you have this newly added resource in your pool. So this is basically a standard computer with some configuration added by the client depending on your requirements. But what it means is that it's not going to have the best cooling system available. It's just going to have a simple processor with some fans attached to it. So in the conditions where they start to get hot, then inevitably the performance is going to degrade. So you cannot know that this is going to happen or not going to happen at any given moment of time. So that's one of the things that affect the fact that you cannot you cannot see how much time the algorithm will take to execute, and that's why you always give an approximate. How do we estimate the algorithm complexity and execution time? By simply counting the CPU instruction based on the input size, what we've been doing till now, by talking about the input size and the type of algorithm that we are using. Continuing a bit example, talking more about mathematics right now, coming to BigO. And BigO has some properties. And for example, the factor, one of the principal characteristics of using BigO is that the factor can be dropped. What does this mean? So basically, we are going to see more examples coming on, in which we're going to see various methods being used at the same time. But for example, here, what it means when we say the factor can be dropped is that, let's say that we have by factor, in this case will be the 3, and this is the function that is happening at the moment. So what it means to be, when you say that it can be dropped, is like we can say y equals 3x, and we drop the factor, so it's just a function of x. In this case, it will be something like a linear function. Or for example, y equals x squared divided by 10. We drop the factor the first time, will give you o, and function of x squared in this case. So we can drop the factor all the time. And this applies for longer, for the sum of longer functions. For example, another way here, we have y equals to 2 times square, 2 times x squared plus 5x, 5 times x, times logarithm of x plus 10 times x plus 2, which it will equals to the bigger function, to the fastest growing function in here, in this whole sum, which it will be the x squared. So first, as a matter just for depicting, we get O 2x squared. But we can also go a little bit more and drop the factor, which will be the 2 here. So we end up with something like the function of x squared, or x to the power of 2 in this case. Some other examples will have y equals to x plus 5. We drop the factor, in this case it will be the 5. We end up with function of x, which will be linear. Same thing underneath, we have y equals to 5x plus x cubed. We drop the first part, which will be the 5x, and we end up with x cubed, with the function of x cubed. And we have then we have y equals to x times logarithm of x plus to the factorial of x squared divided by 1000. The fastest growing function here will be the x squared, and will be, by eliminating the first part, the x times logarithm of x, and the factorial, the factor which will be under the x squared, which will be the 1000, we end up with O x squared. Same thing with the last one, with the factorial, like y equals to factorial of x. This is translated, the factorial of x translate to x to the power of x. And that's why we end up with a function of that, approximately. And continuing on, when we have as simple examples of simple constant time and some linear time. For example, when talking about constant time, we had some memory assignment, variables, array elements. Every time you're assigning something or declaring something, or when your code is accessing memory, when calling a method, when you are creating an object or constructor, an arithmetic operation, if then else statements, printing. All of these are examples of constant time because they take the same amount of time every time they are called. And then we have linear time, which is basically when an array is being copied to maybe another array, or when we are iterating a collection, or when we are doing for each or loops in general. This is basically an operation that is linear time because it's going to grow depending on the input size of the function. All right, so we arrived to the middle break. There are any questions?
Yeah, we have one question in the chat. Let me show you. It's what about O from n factorial?
Well, this was mentioned before, and it's basically in this case here, when we have the factorial, it translates to a function of x to the power of x. It's an approximation, but it's gonna look like that.
Yeah, thank you. I hope that answers the question. If not, please post another question, maybe more deep question about that, if you wish. I think we can proceed.
All right. Okay, continuing with now some examples about related to Java in this case, to BigO. We have an example code here, snippet of code, in which we have a variable declaration assignment, an iteration, and comparisons because we're using if statement here, and assignments because what is happening is in the if statement, and one return at the end. So this is all, it can be all seen here as the kind of explanation of the function, what this is doing in this line where it says fn equals 1 plus 1 plus 1. Well, it's basically mentioning that every time we see a 1 is a constant time, every time an n is linear, and which ends up being 5 plus n, 5 plus 2n, which when we drop all the factors, we end up with the fastest growing function again, which it will be only n in this case, which it will translate to the function being linear. And then we have here the explanation. For example, if the execution time of a function with input of say 1 millisecond, 1 mil is 10 milliseconds, the execution for an input of 2 is 20 milliseconds because it's just doubles the execution time. Basically, that's it for a linear. That's how a linear function will look like. In this case, we will have a quadratic function because here in the snippet we see two uses of two for loops. And this translates also in this type of explanation here, in this sum of functions happening within the code, which at the end, after dropping all the factors, we end up with function of n squared. And here is a small explanation as well. It's just translate to the same thing once we solve the equation. Basically, one impulse of size 1k is equals to 10 milliseconds of execution time. When we have 2k is, in this case, 40 milliseconds, because we need to apply this type of equation. And maybe it's not very clear when it comes to using math here, but maybe for those of you who are more used to using code, then here it will make more sense if you just look into the first internal to the first external pair of for loop. So basically, let's say that the E here, we have the first external element coming from the first for loop has a child. So then this child need to be iterated in the internal for loop for any given elements depending on the input. So that, let's say the internal for loop ends, so the external for loop needs to continue to the second element and then coming back to the internal one. And this will happen n amount of times in the internal one and in the external one. So that's why it's n to the power of 2. And this type of function will degrade greatly depending on the input, also in the complexity of the code that is happening inside. And then this is another example of the of using n square method inside. In this snippet is just abstracting the complexity, but at the end is just the same kind of example. And this is the part where I was expecting to come to arrive, because this is more about real life scenarios. Normally, we are not using it in the way I explained before, but it's good to have in mind to know how more or less the math and other function it looks when we apply a more mathematical approach. But it's also necessary when we have it in the real life scenario here, because now we can understand more or less what is happening here. And let's say in the real world, no one calculates CPU instruction like that. Complexity of our algorithm is combined from bricks, like constructor. What it means from bricks? Well, basically we have every color here represents a brick. So we will have something like the more internal one. It will be the constant time operation. So something like a print statement here, an if statement, just maybe assigning a constant also, something like that is happening here in the blue rectangle. Now in the one that is like sky blue, this is something like an end linear operation here, because we are using a loop here. And then we have the even kind of green color here, which will add another layer of complexity, which will be another n to the formula. And that's why we see n times n times 1. which will be n squared. We are waiting for your questions in the chat. Okay, yes. The same thing with the other one, with the other brick in the bottom. Here we have an end, a loop, a for loop, which will equals to an end. It is saying that it's a linear time complexity exercise. And then the blue brick, where it says binary search, it will equals to log n. When we combine those two, and we get n log n. So this is all happening in a method, which will be more like real life. So then we will have the total complexity, which will be O coming from here, O n squared plus O n log n. And we need to apply just the same parameter we've been doing before. We stay with the fastest growing factor, in which in this case will be the n squared. So just to explain and give an approximation of how much this method in real life it will take, we say it will take BigO of O n squared. This is more like how will you use it in real life. And you see, we are not taking in consideration the O n log n, and that's why this is an approximation. It's nothing like you're saying exactly how much it's going to take. You're taking basically the worst time that is being done during inside the method by, in this case, the upper brick. More examples about how it will degrade in a specific data structure, in this case an array list, using the Java approach. For example, we have, let's say, we have an array of initial 8 elements, right? And we are adding elements to this array. One thing that is worth to mention is that the add method in an array list is constant. So this means is O1. Adding elements to the array every time gives us a constant time. Now, what happens when the list gets full? Well, basically, Java has their own implementation of this. And basically, when it gets full, it takes the list that is full, creates a new one based on the same size of the previous one, and instead of putting the same size, takes the previous size and add 1.5 times the previous size to the new one. So now, and it copies every element that was before into this newly created list. And then it allows to keep adding elements to this. So then after everything is copied over the newly created list, then it's allowed to continue adding elements, returning O1 constant time again. But what happened during this copying? What happened during this copying of elements to the newly created list? So basically here an O(n) operation happens because you need to iterate during the full list that you had and copy every one of the elements into a new one. So this will be an O(n) operation. And after doing this is how the kind of mathematical translation of this operation would look like, which it will end, and in this is explaining right now what happens if we increase the list 1.5 times, and on average it basically is saying that it won't get full, and that's why it's saying that the end, like the resulting the time will be O1 because it won't get full at the end at the time. But this is not what is important right now here. What is important to have in consideration is what the data structure would do in this case. So I'm talking about the copy operation, which it will end up in being in an O(n) operation happening after a specific amount of time, after the size gets full, and until Java needs to create a new list for supporting new elements. So every time Java needs to create a new list and resize, is doing an O(n) operation, which it will be, of course, impacting the performance. Now, talking about memory consumption. There are some algorithms that require additional memory. Memory consumption is calculated in the same manner. BigO notation can be used here too. For example, merge sort. It's an efficient sorting algorithm, but it requires an additional array of the same size to manipulate data. This means that the merge sorts, the initial data structure, is let on order, and you need to sort this. In this case, the green rectangles you see here, the green squares. Sorry. Then the resulting one, let's say the sorting one, the sorted list in this case will be the blue one. But this blue one is a newly created data structure that is created by the merge sort. This means that it's additional resource that the merge sort is creating for to be used for sorting this list. The merge sort has an performance of n log n time complexity and requires O n additional space. And that's what it means by this. Is fast when it comes to performing a sorting operation, but it requires more space for every item that is trying to order. And this can be seen here in this explanation. If you pass 1 kb of array, it will create 1 more kb of array just to make it order. If you pass 1 megabyte array, it will allocate 1 megabyte more just for the process of ordering. Okay, continuing, we have here some examples of some data structures and algorithms and how the BigO notation looks for each of them. For example, we have stacks and queues. They have a notation of BigO notation of 1 for insert and removal of elements. When we're talking about list, you have the array-based list, and you have an 01 performance time for insert to the end, get and update of elements. For delete from the end of the list, it will take also 1n. Now on 01, sorry. Now when we are inserting to the start and removing from the start, it takes on end complexity because it will specifically for Java it will need to look for this index, and it will take an iteration, basically an iteration operation for this to happen. For linked list, you have the all end time complexity for inserting, getting, and updating values, and also for deleting from the middle and end. Now, when it gives you good performance, constant performance, is when using from the start. And I know there are some implementations outside of Java that also give you the same performance on the end. Now, right now I can't remember the exact implementation of those languages, but I think that there exists for that. Now, when talking about trees, you have the tree matrix set SQL index, for example. They have a performance of O log n for insert, read, update, and delete operations. You have the hash tables, hash map, hash set, and concurrent hash maps implementation of the table interface, which give you a performance of one constant time for inserting, reading, updating, and deleting. And the heap, the priority queue, for example, it give you a performance of BigO of log n for push and pop operations. Binary search, like mentioned before, give you a log n. Sorting, quick sort, for example, for sorting, quick sort and merge sort are n log n. For example, those are another example of those are for sorting are bubble sort, select sort, insert sort, but they give you O n squared. And you have also the k max min elements from the array, and they give you this type of a sum of O of n plus k log n. If you wanna read more about general case sorting and BigO notation, I would really recommend reading something like Cracking the Code interview. It has a whole chapter dedicated for BigO notation, and they explain all of these in more detail, giving way more examples. In this PPT, in this slide, it's about general case sorting, which explains, which basically states that the performance of BigO and log n, there is there is a proof that no general case algorithm can work faster than this one. For example, quicksort and merge sort, and the proof is depicted in here. But this is more about tree type theory at the moment, and how it works when it's talking about leaves and parents. I will leave this for maybe separate investigation later. But if any of you are interested in knowing why is the proof and so on, explain here. I'm not gonna go in detail right now as I'm running out of time. And we have some FAQs here if you guys are interested. Do algorithm with lower order work faster in all circumstances? No, because notation lets you see which algorithm will be faster when the size of the input goes to infinity. On a small dataset, slower algorithms may work faster. An example is like, for example, it's faster to sort an array with 16 elements using simple Google sort, not quicksort, and it's basically for how the algorithm is written, basically what it's doing inside. If you're interested, just refer to the implementation of the bool sort and quicksort. And how to approximate how much time an algorithm will take. And this basically you can use a formula like this for making the approximation of how much the algorithm will take. And do you need to know algorithms to work as a backend developer? This is a funny one. Is basically, I would say that you have to know basic algorithms and data structures. Advanced algorithms are very rare on real projects. This is true, specifically the last part, but in fastest depends on basically the role you're taking at the moment. If you are a senior developer, team lead, and also you're trying to work in a big data project, something in which you're going to be using millions or billions of data or payloads, you will need to basically know this theory. You will need to go even deeper into kind of using binary search approaches, trees, sorting algorithms, combination of sorting algorithms, and also how to use properly the databases depending on your features. For example, if to use relational database using an index, or no relational database makes sense for you given the right use case that you may have. But knowing all of these performance type theory will for sure make you a better engineer in the long run. Some recommendation here. If you're interested, you can study binary heap, binomial heap, and all of these type of data structures. One of the also, if you're working into trees right now, or you're going to be using trees in the future, it's recommended that you learn the breadth first search and the depth first search approaches, and they are very useful depending on the use case, obviously, as you have, but they are very useful and good for expanding one's knowledge and view of how to deal and treat trees. The sorting algorithms, like of course, it's really needed to know quicksort and merge sort, and there are a lot of APIs already implementing those. maybe a different approach of those, but at the end they are implementing those. It's very rare in real life to need to implement the quicksort or merge search by yourself. It would be kind of debatable having to do so in a project without any library, but it can happen. You never know what specific need you will have in your project, so it's worth to know that they exist and maybe read them once or twice to know how they work internally. And if you need to come back to them, it's going to be easier just to catch on and fresh out some knowledge. And we've arrived to the end of the presentation right now. Maybe 5 more minutes for questions.
Yeah, thank you. We are going to the end. So if you have any questions, you have the last chance to post it in the chat. And yeah, one question we have now, I'm showing, is the following. Bubble sort has O from n square, but quick sort is better. Do you know an algorithm with O from n square or worse, and there is no better algorithm?
Do you know algorithm with O with n square or worse? I'm not sure if I understand that.
I think it's about like for example, here we have different algorithms for sorting, and for sorting we have bubble sort with like O from n square, and we have better algorithms. So maybe there is some operation like not sorting but something else that we have only algorithm with O from n square or worse, and there is no better algorithm for doing something.
Um, if I understand it properly, like the question is that if there is anything worse than n square, maybe using a brute force algorithm could be like checking every element using like through maybe a very bad implementation, but it's like a 3 or 4. I've seen in my life 3 for loops, one inside the other one, and some search operation inside. So that's something like that will be very bad. But yeah, that would count, I think, as brute force. I don't know if that's what the question was about.
Yeah, someone have another comment like, is there a bad algorithm without any alternatives?
Is there a bad algorithm without any alternatives? Um, mm, mm, mm. I will say that it depends on the, like I said till now, on the use case that you have. Usually at this moment there is basically a solution for most things. I'm not saying that you don't have a very specific use case, you may have. But if there are not any alternative, any good like documented alternative for your specific use case, I wouldn't say it's bad, but is just complex. I would say like it will require maybe consulting different solutions, maybe combining some solutions and strategies to achieve something that is not bad, that is not performing bad.
Yeah, I agree. It really depends on the on your use case. So I guess there are no any new questions. Uh, if we don't have any questions, I want to say thank you to you, Joaquin, for your presentation and for your explanation of BigO. And I want to thank you, all of you guys who participated in this meeting and who are asking us these questions. Thank you, and we will see you next week.
Thank you very
Bye.
much, and thank you for the invitation. Bye bye.
Bye.